Hello, and welcome to another video about linear algebra. My name is Patrick Naylor, and I'm one of the instructors for Math 235, along with Graham Turner. In this video, I'd like to talk about coordinates for vector spaces and the change of basis matrix. In my opinion, this is one of the more difficult topics covered in Math 136. We'll be using these ideas a lot, so I thought it would be a good idea to make a video and hopefully clear some things up. You can find this material in section 4.3 of the textbook. Okay, so we'll begin with the following definition. Suppose that V is a vector space, and B, consisting of elements B1, B2, all the way up to Bn, is a basis for V. Consider an element x in V. Since B is a basis, for some real numbers, alpha 1, alpha 2, all the way up to alpha n, we can write x as equal to alpha 1 times b1 plus alpha 2 times b2, all the way up to alpha n times bn. In fact, this representation is unique. The coordinate vector for x with respect to b, or the b coordinate vector of x, is the vector alpha 1, alpha 2, all the way up to alpha n in Rn. Because we've picked a basis, this is really all of the information that we need to reconstruct the element x. Something very important to note here is that x is an element of the vector space V, but the b coordinate vector for x is a vector in Rn. They both represent x, but are elements of different vector spaces. This distinction is very important when you're trying to write down a proof. Something else that's important to note here is that in this case, the basis is more than just a set. In order to reconstruct the element x, we need to know the order of the vectors in the basis B. When you're doing your calculations, always fix an order of the basis. Okay, let's look at a quick example. Suppose that V is P2 of R, or in other words, the vector space of polynomials of degree at most 2. Consider the basis B for V given by x squared minus x, 2x minus 1, and the constant polynomial 2. You should check that this is a basis. In this example, we'll compute the b coordinate vector for the polynomial x squared plus x plus 3. If you're following along, pause the video and see if you can do this for yourself. Well, by inspection, we note that we can write x squared plus x plus 3 as the following linear combination of these basis elements. X squared plus x plus 3 is equal to 1 times x squared minus x plus 1 times 2x minus 1 plus 2 times 2. So, the b coordinate vector for x squared plus x plus 3 is just the vector 1, 1, 2 in R3. Again, we see that x squared plus x plus 3 is just some polynomial in the vector space P2 of R, but its b coordinate vector is actually a vector in R3. Okay, well, suppose that we had an element x in our vector space, and we knew its b coordinate vector. Could we find its coordinate vector with respect to a different basis? The answer is yes. We do this via a change of basis matrix. The definition we need to know is the following. Suppose that V is a vector space, and B is a basis, let's say consisting of elements B1, B2, all the way up to Bn. Further, suppose that C is some other basis for V. Then the change of basis matrix from B to C is the real n by n matrix whose columns are the C coordinate vectors of B1, B2, all the way up to Bn. We denote this with a capital P with a script B and a script C on either side. You may have seen these vertical lines before, but here they're just to separate the columns of this matrix for clarity. The important thing about this matrix is that it satisfies the following identity. The change of basis matrix from B to C times the B coordinate vector for x is equal to the C coordinate vector for x. Note that this matrix is an n by n square matrix, and coordinate vectors are n by 1 vectors, so this multiplication does actually make sense. I like to think of this matrix as an input-output machine. If you start with the b coordinate vector for x, and you multiply it on the left by this matrix, you get the c coordinate vector for x. In other words, it inputs b coordinate vectors and outputs c coordinate vectors. This matrix is very important, so review section 4.3 for the proof of this fact, or if it just seems at all unfamiliar. Let's wrap this discussion up with just one more example. Let's let V be P2 of R as before. Consider the basis B as before, with elements x squared minus x, 2x minus 1, 2, and a new basis, C, which is just the elements 1, x, and x squared. In this case, let's compute the change of basis matrix from B to C. To do this, we need the C coordinate vectors of each of the elements of B. We can easily check that the C coordinate vector of x squared minus x is 0, minus 1, 1. Also, the C coordinate vector for 2x minus 1 is just minus 1, 2, 0, and the C coordinate vector of 2 is just 2, 0, 0. Putting these columns next to each other in the right order gives us the change of basis matrix given there. As I mentioned earlier, when you're doing these kinds of calculations, the order of the elements in the basis must remain fixed. If we want, we can compare this to our previous calculation by computing the C coordinate vector of x squared plus x plus 3 using our new change of basis matrix. By the formula on the last slide, this is equal to the change of basis matrix from B to C times the B coordinate vector for x squared plus x plus 3. We just computed this change of basis matrix, and we computed the B coordinate vector for x squared plus x plus 3 in the last example. If we perform the multiplication, we obtain the vector 3, 1, 1, which you can verify is in fact correct. We'll be working with coordinates a lot from now on. It's how we do calculations in abstract vector spaces. In general, there may not be a preferred choice of basis for a vector space, so it's important to know how to move between different bases. If any of this stuff looks unfamiliar, have a look at section 4.3 in the textbook. Well, that's all for now. Study hard and good luck.